Okay, this is Mrs. Carreri's sort of solutions video, if you'd call it, to Unit 2 Progress Check, MCQ Part A. I think there was like 21 questions. I've already kind of prepped this PDF so that the solutions discussion will not be as long. It's under AP Classroom Assignments, so you can see all this writing. Students typically don't like or don't, for whatever reason, want to do work off to the side of MCQ. It's not supposed to be something, at least on the AP exam, that you could just know intuitively. You may have to do some math. You may have to draw free body diagrams and so forth. All right, this picture here is going to apply to both two questions. We have a block MA and a block MB. They tell us that its string is taunt, which means there's a force of tension in that. If it wasn't taunt, there would not be force of tension. They also tell us at time equals 0, block A is sliding up the slope as B falls, okay? And they're slowing down. So it starts with an initial velocity, and then as it slows down, MA is eventually going to stop and then slide back down, okay? So obviously mass of A must be larger than mass of B in order for that to happen, okay? We'll get to the free body diagrams in just a minute. You didn't have to draw a free body diagram to answer the first question. And I recommend that you read the problems before you start diving into the work. So number 1, if the mass of block B is 2 kilograms, the gravitational force exerted on block B is most nearly what? So force, the gravitational force, what is the symbol for gravitational force? It is Fg. What is the equation for Fg? Mg. Now, we haven't talked about this yet, but it says most nearly. In all of the AP problems on the exam, I want you to use 10 for little g. Little g approximately is 10 meters per second squared. Makes the math easy. Most of these math problems you can do without a calculator. 2 times 10 is 20. Answer is C. Pretty straightforward. Didn't have to do any work. I could have done that in my head. No calculator necessary. Now, number 2. The two blocks eventually stop and they reverse directions. Which of the following graphs best predict the acceleration of block A as it moves up and then down the rough inclined surface? The word rough implies there is friction. We want, and then they told us that the positive direction points down the slope. I don't have an option. Positive direction points down the slope. So negative is up, positive is down. So I have free body diagrams of block A. I cannot answer the question about acceleration unless I think about the forces acting on the block. And again, I want to know the acceleration up or down the ramp. And they tell me on the way up, it's slowing down. Okay, so free body diagram in black to the left. There's the free body diagram of block A on the way up. So black dot represents MA, force normal up, force of gravity. Again, I don't like drawing my free body diagrams at an angle. I think I have to see it in what I'll call, this is the new x-axis, right? Come on. This is my x-axis. All right. So I can't see it at an angle. That's just the way I am. So this is my x. Oh, come on. What are we doing here? This is my x-axis, and this is my y. Okay, so that's just the way I do it. I have a lot of people find that that's helpful to turn it sideways and look at it this way. The graders will know what you're doing. Okay. At any rate, force of gravity is cattywampus to the left, the way it's drawn, and that means that there is a component of gravity that's down the slope, and that is the Fg sine theta, and there's a force of gravity that's perpendicular to the incline, that's Fg cosine theta. Force of tension is pulling towards the right or up the ramp, and If it's a rough surface, which they told me it was, there's friction involved. Friction wants to oppose motion, so friction has to be going down the ramp while the block is going up the ramp. Okay, so there's the green, and that's important because you're going to see why in just a minute. Then if you look at the free body diagram down the ramp, again, force gravity sine theta is pointing down the ramp parallel to the surface. Force of gravity cosine theta is perpendicular to the surface. There's force normal. Force of tension still there, but this time force of kinetic friction is now up the ramp because now I'm sliding down. So acceleration is impacted by that flip of force of kinetic friction. In one case, force of kinetic friction works with the force of gravity sine theta, which is the component of gravity parallel to the incline. And in the other case, the force of gravity and sine theta works against the force of kinetic friction. Now let's look at what they told me. They told me I was slowing down on the way up. They told me up the ramp is negative, so velocity is negative. I must be slowing down, so acceleration has to be positive. So we know acceleration. I do not know why it's doing that. We know acceleration has to be in this direction, which is positive, because I'm slowing down. So it is pointing down the ramp. It comes, and that makes sense because I'm slowing down. I come to a stop, and now my velocity switches sides, and now I'm going to accelerate down, and I'm going to speed up. I'm going to speed up down the ramp. So in the case of acceleration, which is positive, which is down the ramp, if you look at up, acceleration up is greater than acceleration down because force of kinetic friction now is working against me. And they're both positive because they're down the ramp. And I've got to go find those graph like that. A is wrong because acceleration is positive, but it doesn't change. And we know that force of kinetic friction flips and then works against us on the way down. B is correct. It's positive on the way up and it's larger on the way up. It's still positive on the way down, but it's smaller because of that force of kinetic friction that now works against me. C is correct at first, and then they show that the acceleration became negative. That is not the case. I would now have a positive velocity and a negative. I would be showing the block slowing down on the way down, and that's not the case. It is speeding up. There's no indication that I'm sorry, it would be slowing down again. Yeah, and that it came to a stop. So how can it slow down again after it had come to a stop? D, if you picked D, you weren't paying attention to number one, the directions and what they gave you as the signs of the incline. In addition to that, they told you the velocity up the ramp was negative and it's slowing down, and it can't be slowing down if acceleration is negative and velocity is negative. Move it on. A 5 kilogram object is released from rest near a surface of a planet, such that its gravitational field, what is the gravitational field? It's little g, is considered to be constant. So g is constant. The mass of the planet is unknown. After 2 seconds, the object has fallen 30 meters. Air resistance is considered to be negligible. What is the gravitational force exerted on a 5 kilogram object near the planet's surface? Force of gravity is what they're asking for. Gravitational force equals question mark. It is equal to the mass times g on that planet. I don't know this planet's, it's not planet Earth, so we got to figure out what the acceleration due to gravity is. They told me it was released from rest, velocity equals 0. Okay. They told me that time after time equals 2 seconds, that delta y had equal, I'll call down positive, 30 meters. So I have enough information to solve for the acceleration that the object experienced, and the acceleration is due to the force of gravity. That's the only thing that's acting on it. And I can then determine the little g. So let me see what equation I use, number 3. Delta y equals 1/2 at squared. The initial velocity is 0, so that second term cancels out. A equals 2 delta y over t squared. And if you plug in the values, again, most of the time you can do this without a calculator. 2 times 30, so I got 60 divided by time squared. How much time did they tell me? Time equals 2 seconds. And so that is 4, and 4 divided by 60 is 15 meters per second squared. So that is the acceleration that the object is experiencing, and that is the acceleration due to gravity on that planet. So now I can go and determine its force of gravity, which is 5 times 15, which is 75 newtons. Okay. Don't solve these problems until you've read everything. The first thing you might be thinking, oh, it's a coupled motion problem. I'm going to go and draw a bunch of free body diagrams. And then you read the question, you're like, oh my God, I just wasted a minute. A block of mass M is attached to a modified Atwood machine and is accelerated upwards at a 3A, that's the acceleration, 3A, by a constant force V naught. What is the weight of the block? Definition of weight. Weight is equal to Fg, which equals mg. They did not tell you you weren't on Earth, so you will assume you're on Earth. Oh, we don't even have to calculate a number. Mg is the answer. So definition of weight, mass times acceleration due to gravity. Doesn't change unless you move to a different planet. I got a picture, guy's on a ride. The amusement park ride shown above takes the rider straight up a tower and then releases an apparatus holding seats. This apparatus free falls back to Earth, free falls, and is stopped safely right before the ground. Which of the following indicates the magnitude of the gravitational force? What is gravitational force? Fg, exerted on the rider of mass m on the way up and on the way down. Well, last I checked, the Earth doesn't change whether I'm going up or down. So the magnitude of the force of gravity on the way up is mg. On the way down is mg. No matter what, force of gravity is mg. Okay. This is one that we went over in class, number 6. I have planet X and planet Y. I have a graph. The graph is a position versus time curve of an object that is released from rest, so velocity equals 0, and then it is dropped to the ground, and the position decreases with time, okay, and eventually hits the ground. One of them gets to the ground in just over 6 seconds, and one is just over 4 seconds, we'll say. Which planet exerts a greater gravitational force on the sphere, and what evidence supports this? They're identical spheres, they have the same mass, it wouldn't matter anyway. Okay, no, it would matter, excuse me. Gravitational force equals mg. They told me they're identical, so mass is the same. All I really need is which one has the largest g. Well, if you look at the graph, it was dropped from rest, so the initial velocity is 0. And then the time to reach the ground is lower or less for planet Y. So I know it by using UAM equations, the time, again, initial velocity is 0. I can solve for time using my second UAM equation. T equals the square root of 2 times delta y over A. Both delta y's are the same. And the time for Y is lower. Therefore, A on planet Y has to be bigger because it's in the numerator. So acceleration due to gravity on planet Y has to be greater. All right. Now I got to figure out which one gives me the right explanation. So planet X, no. So cancel and move on. You know A and B are wrong. You're saving yourself time. Now, you've got to pick between C and D. Planet Y, because the area under the curve is smaller. The area under these curves, area is height times base. The units of the area of these graphs are meters times a second. What in the world is a meter second? I don't know. So that doesn't make any sense. Planet Y, that is correct. We've already figured that out because the magnitude of the slope of the curve increases at a faster rate. Acceleration is change in velocity. Velocity is the slope of a position versus time curve. So you can see that the position versus time curve tangent lines increase their slopes at a faster rate for Y than X. Hope that helps. All right, number 7, two identical, I'm going to read it, then you got to draw a picture. Okay, you can't solve this without a picture. Two identical blocks, block A and B, they have the same mass, by the way, that's what that means, are placed on different horizontal surface. Blocks A is initially at rest on a smooth surface, no friction, while block B is initially at rest on a rough surface, friction. They will both be exposed to a constant horizontal force of magnitude F naught. Okay. After the force has been applied for the same amount of time, the final velocities are measured and they're found to be VA and VB. Which of the following claims is correct about the relationship between velocity A and velocity B, which is the velocity final, essentially. So off over here to my right, I have a picture of both. I've sketched quickly. A block pulled by F naught, A on a smooth surface, B on a rough surface pulled by F naught. I have some time t, which is the same for both. Initial velocities are the same for both. So the 5, 4, 3, 2, 1, right? I'm trying to find final velocity and how this force or friction impacts this final velocity. So you've got to have acceleration in order to answer that question. You know initial velocity for both, the time is the same for both, but you've got to figure out acceleration for both, okay? So again, I draw a free body diagram of the forces in the direction I care about. Force not to the right for A, no friction. Force not to the right for B, but I got a little kinetic friction to the left. Because of that kinetic friction, the acceleration acting on block, or the acceleration that block B is experiencing is less than the acceleration that block A. Now, that will result in a smaller final velocity for B than the final velocity for A. And you can, again, they have the same initial velocity and the same time. So final velocity is equal to initial velocity plus AT. So that's the value that is less for B, therefore final velocity for B is less. Now we got to go over here and look at our options and figure out what's going on. So we said final velocity for B is less, which means VA is greater because they put A first. So VA is less than this one. VA is less than that one. So I've got to pick between C and D because VA is greater than B, or in other words, B is less than A. So let's look at C. The forces between the atoms in a block and the atoms in a surface oppose the motion of the block and are greater on average for block A. So what they're talking about is frictional forces. Okay, the atoms at the surface and the block. That's the frictional forces. But A has no frictional forces. So that is an incorrect statement. The forces between the atoms in a block and the atoms in a surface oppose the motion of the block. That is true. And they are greater on average for block B. That is true because B has a rough surface as opposed to the other one, which is smooth. So that's why the answer is D and why C is not the answer. Which of the following experiments could be used to determine the inertial mass? Inertial mass. Inertia is the magnitude or the amount an object resists change in motion. And how it's measured is using second law. Inertial mass has to do with F equals ma. Gravitational mass has to do with Fg equals mg. So we're going to look at this. Place a block on a rough surface, lift one end of the surface, and measure the angle that the surface makes with the horizontal at the moment it begins to slide. That has to do with coefficient of static friction. You're bringing it up just enough to get it to slide. So that has nothing to do with mass. Drop the block from the different heights and measure the time it takes to fall. Again, that's UAM, and there's no mass in any of those equations. That's a technique to determine the acceleration due to gravity using that technique. C, place the block on a rough surface. Give the block an initial velocity, VI, and then let it come to rest, which is V final equals 0. Measure the initial velocity, final velocity we know, and the distance that the block moves, delta x, and comes to rest. Allows you to determine acceleration, which then you might be able to determine the kinetic friction, and if you knew the mass, you could determine mu sub k, but that has nothing to do with the mass. Use the mass. We're trying to determine the mass. How about D? Use a spring scale to exert a force, okay? Measure the acceleration of the block and the applied force. So you're looking at the relationship between force and acceleration so that you can find mass. And by the way, that's exactly the same lab that we did in class. So how do you use Newton's second law to find the mass? Number 9. 1,500 kilogram car traveling along a road is hit by a rock. It creates a small crack in the windshield. Which of the following describes interaction between the windshield and a rock? This is the third law of pair. I can tell by the question. The car exerts a force on the rock, but the rock does not exert a force on the car. Third law states they are equal and opposite forces. B, the rock exerts a force on the car, but the car does not exert a force on the rock. Again, same reason why A is wrong. C, the car exerts a force on the rock and the rock exerts a force on the car. All right, good. They got that part right. However, the two forces are not equal in magnitude. Third law says they are equal in magnitude, opposite in direction. Hence why D is correct. Moving on. Number 10. Two objects, X and Y, move towards each other and eventually collide. Object X has a mass of 2m and is moving at a speed of 2v0 to the right before the collision. Object Y has a mass of m and is moving at a speed of v0 to the left before the collision. Which of the following describes the magnitude of the forces the objects exert on each other when they collide? So here's a picture. I got a picture that I drew. I have 2m, the mass of X, moving to the right of 2v0. I have the Y object, M mass, moving to the left of v0. And we want to know, the question had to do with the forces acting on each other when they collide. These third law pairs, even though I didn't draw that to scale exactly, states that the object X puts a force on Y, object Y puts a force on X, and they are equal and opposite in magnitude. It has nothing to do with the speed of them. It has nothing to do with the mass of them. It will impact the acceleration that they experience. One's going to accelerate to the left, one's going to accelerate to the right, and that's because of their masses being different. But it will not impact, the forces are, third law states, are equal and opposite. So here are all of our options. They're going to try to trick you up by using those differences in mass. The force exerted on X by X on Y is to the right. And by the way, they did tell you which direction. So X does put a force on Y to the right. So all of these, except for D, X on Y is to the left. So that is not acceptable based on the problem. At any rate, it's a third law pair question, and it is C, and I hope you see it. If not, please come talk to me. So this is force of gravity this way. All right. A block is placed on an incline. It remains stationary, so it's at rest. A student makes this claim. Block remains stationary because as gravity tries to pull down the ramp, gravity is impacting the block down the ramp by Fg sine theta. The block will exert, so gravity is acting on the block, but the block is going to exert, they're stating, an equal and opposite force on itself. So they're saying that the block is going to create a force on itself. Is the student's claim correct or not? Just so you know, no object can create a force on itself. We cannot, it has to be an external force. We have internal forces that we can do, but we can't put an external force on us. So the student is incorrect. So if you recognize that, you can skip A and B immediately and determine if C or D is correct. No, Newton's first law states that the block's inertia must cause it to move down the ramp. What does the first law state? First law states that an object wants to stay at its current state of motion unless acted upon by a external force. Now let's read this again. First law states that the block's, let's call it mass, must cause it to move down the ramp. No, it wants to stay at the current state of motion unless a net force is acting on it. Let's read the third, or the letter D. Newton's third law states that the block cannot exert a force on itself. That is true. It has third law. Third law pairs are always two objects. I don't know if I did the greatest job explaining that. I hope you understand. 12. Students connect a spring scale to a block on a rough horizontal surface. The students use a spring scale to measure the magnitude of the force needed to pull the block at a constant speed. That's pretty important phrase. Which of the following statements explain why two forces exerted between objects are equal in magnitude? So I'm going to draw a picture of the situation, okay? So down here is my picture. I'm going to reread the question. I got a block, I got a spring scale. What is a spring scale? This is a picture of my spring scale. Spring scales essentially is a fancy way, actually, if we didn't have any force sensors in our classroom that gave us a digital readout of force, we would use a spring scale. And a spring scale is just a manual way to measure the force. It's not as accurate as a force sensor, but it is capable of telling you how much force I pull on that block. And while we pull it across a rough surface, so that means there's friction involved, we're going to do so at a constant speed. And what does that mean? Acceleration is 0. So if I look at the free body diagram of the block, which is this free body diagram, I will have force applied, which I'm measuring from the spring scale, to the right, and I have force of kinetic friction to the left. Force of kinetic friction to the left is going to be the same magnitude of the force applied to the right because they told me acceleration was 0. So those two are equal. We have a force normal from the table up and force of gravity acting on the block down. Now, if I look at, I now have over here the forces. I'm just looking at the forces from the table that are acting on the table relative to the surface of the block, okay? Now, there's a force normal that the block puts on the table downward, correct? Well, also, if the kinetic friction on the block is acting to the left, there is the same force of acting on the table that acts to the right. And those are third law pairs, just as the force normal on the block on the or from the block on the table is a third law pair. Okay, now let's go read the statements. Which of the following statements explain why two forces exerted between objects are equal in magnitude? They're talking about third law pairs. The gravitational and normal forces exerted on the block, because they're Newton third law pairs. Gravitational force and normal force on the block are acting on the same object. That cannot be. Third law pairs are on the two different objects. Force of gravity on the block, third law pair, is the force of gravity that the block exerts on the Earth. B, the frictional force and force exerted, okay, the frictional force and force, so they're talking about FA, the force applied, and the force of kinetic friction by the spring scale. They're Newton's third law pairs. Well, again, that is acting on the same object. Cannot be a third law pair on the same object. C, the force normal and the frictional force, okay, got that, on the block. Because objects always exert forces of equal magnitude on each other. Well, force normal is perpendicular to the force of kinetic friction acting on the block, and that is not opposite in direction, and I have no idea what the magnitude is relative to each other of that. So C is all jacked up and incorrect because of specifically the perpendicular issue. D, the frictional force that the block and the surface exert on each other, okay, the block and the surface exert on each other. there are two frictional forces. One's acting on the block and one is acting on the table, and they are equal in magnitude and they are opposite of one another. So D is the only thing that makes sense. Okay. All right, we talked about this in class, but I'll talk through it again. We have a launcher. It's on this platform. The platform has no friction. The launcher is going to launch that ball to the right. Just imagine going out to the shooting range and shooting a 12-gauge shotgun. That shotgun's going to kick back to your shoulder, and if your shoulder wasn't there, the shotgun would take off. Same thing with this launcher. The ball is going to take off to the right, but the launcher is going to take off to the left. The issue is that the launcher's mass, I got to go look at it, is twice that of the ball. Okay, so the ball is going to land a distance D. The launcher is going to land some distance away, okay, because nothing's making it stay on that platform. It had to have friction in order for it to stay on that platform. So let's look at A and see if we can figure out if it's right or wrong, and then try to figure out what we have to do to answer this question correctly. The launcher will not fall off the platform because only the ball receives an applied force. Incorrect, because Newton's third law says if the launcher puts a force on the ball puts a force on the launcher, and those forces are the same. B, launcher will fall off the platform and land a third the distance. I don't know yet, but that's a possibility. C, the launcher will fall off the platform and land half the distance. Obviously, you know that's correct, but we got to figure out how to answer that. D, launcher will fall off the stand and land the same distance. I have to decide between B, C, and D. Okay, this is now it's a projectile. It's a horizontally launched projectile. We're asking something about what happens in the X direction on the launcher. The only thing that matters in the X direction of a projectile is delta X equals V X T. Remember 5, 4, 3, 2, 1 in the Y, and 3, 1, 2, 1 in the X. 3 variables, 1 equation. I need 2 of the 3 in order to solve for the other one. So let's look at the variables. We have delta X, which for the ball is D. And then we have the other 2 variables, initial velocity in the X direction and the time. The time it takes to hit the ground is determined by what is going on in the Y. And the time for both the ball to hit the ground and the launcher to hit the ground is identical. Mass has no impact on the time it hits the ground. Prove it to yourself using your Y 5, 4, 3, 2, 1. So I need to understand what the initial velocity is of the ball and the launcher after it is launched, and how the mass may or may not have impacted it. The initial velocity of the ball and the launcher was 0 in the X direction, and then all of a sudden a force got applied to it for some period of time. Those forces are identical, okay? They're identical to one another. So if I use that F equals ma relationship to look at the acceleration is equal to force over m. Well, the acceleration for the ball is going to be twice the size of the acceleration of the launcher because the mass is smaller by half. Okay, so it's the factor of change problem. So 5, 4, 3, 2, 1, velocity initial of the ball, and the time the time that the launcher and the ball are impacting each other with those forces is identical. So force is the same, initial velocity in the X direction is the same, the time is the same. You'll find that the final velocity of the launcher is half the velocity of the ball. And that's because the mass is twice as big. And notice the mass is on the bottom. So it's C, because once I know that a velocity, or have an idea that the initial velocity in the X direction of the launcher is half the velocity of the ball, I now will go half the distance. That's a tricky one. I'll agree with that. Number 14, I got a block. It's on a rough surface. I'm pulling with a constant force FP at an angle theta above the horizontal, as shown. If the force P is constant, but I start to increase theta, what is true sometime later? Now you have to draw a free body diagram, and you must break up those forces. Okay, so look at the free body diagram. I got force of gravity down, not going to change no matter what happens to theta. Force normal up, force peak sine theta. Well, force normal is going to change. If theta goes up, sine theta goes up, and force normal goes down because they've got to equal FG, okay? Now, let's look at the x direction. If theta goes up, FP cosine theta goes down, right? Yes. And then that could impact my acceleration. So I don't know what they're asking. Let's go look what the questions are. The force of friction between the blocks and surface will increase. Okay, what's the equation for force of friction? Force of kinetic friction equals mu k, which equals Fn. What is Fn? Fn is equal to mg minus Fp sine theta. Okay, I have to evaluate that. So if I look at this right here, mg is not going to change, but theta is going to go up, sine theta will go up, and I'm subtracting it. So as theta increases, force normal goes down, which means force of kinetic friction goes down. Wrong. B, force of friction between the block and surface will decrease. I just proved that above. I'm done with that problem. I would not even look. I scan C and D, but don't waste your time. But here, the weight of the block will increase. The weight of the block will decrease. Theta has nothing to do with the weight of the block. The weight of the block will only change as if you move planets. They did not tell us that. Weight is defined as m times g. Satellite orbits the Earth. The only force acting on the satellite is the gravitational force exerted by Earth. Here's a picture. Here's an Earth, little teeny Earth. Here's my little satellite flying around in orbit. And the only force is FG, which is pointing towards the center of the Earth, just like as if I was standing on Earth, points towards the center. That's the only force. So if you look at the sum of the forces acting on the, oh, I don't like that. If you look at the sum of the forces acting on the satellite equals MA. Well, what's the only force acting on it? We'll call it positive, mg, okay? It equals the mass of the satellite times the acceleration of the satellite. And you find that the little g is now equal to the A. So the acceleration of the satellite, I know it's hard to imagine. We'll get into this in greater detail. The acceleration on the satellite is the same as little g. Now let's look at all the things. The gravitational field strength, what does that word mean? That's G, is unrelated to acceleration. Not in this case. The gravitational field strength and the acceleration is the same. Gravitational field strength is smaller than the acceleration. No, we just proved that it was equal to. C, the gravitational field, little g, and the acceleration point in the same direction. Net force always has to point in the same direction as the acceleration. So that is true. G points towards the center and it's accelerating towards the center. It's actually going to be, okay, never mind. I'm not going to confuse you on that. All right, the magnitudes of acceleration and the gravitational field strength, little g, A, are equal. Sure enough, I just proved it to you with that equation. 16, the object is at rest on the ground. The object experiences a downward gravitational force from Earth. Which of the following predictions is correct about why the object does not accelerate downward? Select two answers. All right, there's a free body diagram acting on the object. FG is down, F normal is up. A, the bonded molecules of the object are repelled upward by the molecules of the ground with the same magnitude, okay? That's force normal, by the way, what they just described, as the gravitational force downward. That is true. Force normal, which is by the bonded molecules of the two objects pushing against one another, tables pushing up or the ground's pushing up, excuse me, is the same magnitude as the force of gravity, which is a field force acting on the center of mass downward. Now, they restated the comment in A, but instead of using the definition or the interaction of the molecules, they used the word normal force is exerted upward on the ground from the ground. Okay, now look at C. The bonded molecules of the object are attracted downward by the bonded molecules of the ground. That is not true. The molecules have electrons at the outer edge, so does the ground. Those electrons are the same charge, they repel. Okay, the force of friction is, this does not want to slide. Force of friction is not present. The force of friction in this problem is 0. 17. We have something that has to do with a trial and a force sensor reading in newtons. The student uses an electronic force sensor as opposed to a spring scale to study how much force someone's finger can apply to a location. So if you can imagine, I have a force sensor. I can push my force sensor with my finger and I will see how much force my finger can apply. And the data was collected from 2 trials are shown in the above. During which trial, if any, does the finger experience the greatest electromagnetic force? If my finger touches that force sensor and I push on the force sensor pushes back on me. What is pushing back on me? A force normal. What is force normal from? The interaction of the molecules between the electrons in those atoms of my finger and the atoms of that hook, and that is an electromagnetic force. Okay, therefore, that's what they're talking about, force normal. Trial 1, because the finger does not apply a force to the sensor. Nope. If I have trial 1, I have no force normal. Trial 2, because the finger applies the largest force to the sensor. Okay. I don't know what C is. That's not true, and that's not true, D. All right. This one's tricky, but these little fan carts are all over the place on these AP exams. All the fan does is allow you to put a force on the cart. The fan turns and pushes the air molecules. The air molecules push back on the cart. It's a force applied acting on the cart. Okay, so I have a free body diagram that I've got force applied to the right, normal up, force of gravity down. They told me frictional forces were considered negligible in this problem. All right. Which of the following procedures can be used to determine how the mass of the cart fan thing, okay, it's got all kinds of stuff. I can change the masses, all right, how that mass affects the acceleration. They also told me that FA was constant, that the fan could not, it only has one setting, okay? So this is exactly like the lab that we did. We want to know how mass affects the acceleration. So we can change the mass and then we will measure the acceleration. We can change the mass and we will measure the acceleration. This will be constant, all right? It's not exactly like what we did. We didn't change the mass of the cart. You could actually use this data to graph and find graphically the force that was applied by the fan. So let's look at what we have. Measure the mass of the system. Okay, we were going to measure this then. That's what they're doing. And then measure the distance. There was delta x. Some time, there's another variable, which we start from rest, by the way, they told us. So there's the third. So then we would have acceleration. That works. That's a 5, 4, 3, 2, 1 to determine A. And then I have the other two because it started at rest and I know how far it went. That would allow me to get a relationship between the changing mass and acceleration by you got to keep the other variable FA constant. How about B? Measure the mass, activate the fan, use a meter stick and stopwatch to find the initial and final speeds. That's a problem. How in the world are you going to use a meter stick to find the final speed of the system? Meter stick, last I checked, doesn't have the ability to determine the instantaneous speed after some time. You can't get V final with the meter stick. C, measure the mass, connect a spring scale to the back of the car, and measure the amount of force required to hold the system at rest. So if you drew a picture of that and you drew a free body diagram, you got the force applied from the fan to the right, and the spring scale would be attached to something and holding it in place, which allows you to determine how much force applied is. So you're really only measuring force applied, has nothing to do with because it's not accelerating, so it's 0, so they have to equal one another. So that doesn't help you. D, measure the mass of the system using a balance. Great, we need that. Activate the fan, use a stopwatch to record the time it takes for it to travel before the battery of the fan no longer works. If that were to happen, the force applied would start to decrease as the battery died, and that experiment would be terrible because we would not be keeping the variable FA constant, and we would have to in order to determine the relationship between mass and acceleration. These are tricky and I struggle. Right now that one was straightforward. There's some in the future which I struggle with, so you'll see them. I've got 2 more to go, or 3, let's see. 3 more. Here we go. Hang in there. Object X, object Y. Object Y is at rest. Object X is moving to the right at 2 meters per second. At time 0, the velocity initial of object X is 2 meters per second to the right. It's a smooth surface. The distance between the two is 8 meters. And again, object Y is at rest and has a mass twice as object X. Okay. They're going to ask about a force diagram, but after 4 seconds, but you don't know what's going on. You don't know if if object X is even reached object Y. You have to determine where that object X is at 4 seconds. This is 0 acceleration because they told me that it's constant speed. So the only equation that works is delta X equals V initial in the X direction times time. If I multiply the initial velocity of 2 times the amount of time, which is 4 seconds, I find that delta X is 8 meters. So what you learned is that at 4 seconds, the object X has reached object Y, and now they've collided. So I got to draw a free body diagram of what's going on at the collision. Because the mass of Y is larger than the mass of X, force of gravity acting on it is larger. That means force of normal acting on Y is larger. Okay, so there's the Y direction data. The only other thing is that Newton's third law states that if an object X puts a force on object Y puts a force back on it that's equal and opposite. Third law pairs. Okay, whoops, excuse me. So I got to go find the free body diagram at the collision. A is wrong because it's missing the force applied from X on Y and X on Y on X, excuse me. C is wrong. If you notice, the force normals and gravities are correct as far as the fact that Y has got a larger mass. However, they show that the force from X is smaller than force from Y on X. And third law says they're equal. D might be the one most people want, whichever one is bigger, I can't remember. But anyway, shows that the force from X is larger and the force from Y is smaller, but the normal and gravity are correctly drawn. If I go to the correct answer, you'll notice that not only are my force of gravities correctly drawn and consequently normal forces, Y has a larger mass, but the force from X and force from Y on each other are equal in magnitude, opposite in direction. A student sets up experiment to determine the inertial mass of a cart. How many times we've been approached with this? Student has access to the spring scale, meter stick, and a stopwatch. We got to use our fancy motion detectors to do this experiment. Student uses a spring scale to pull a cart from rest via initial 0 along a horizontal surface such that the reading on the spring scale is always constant. In other words, constant speed. All force, oh, no, that is not constant speed, excuse me. It just means that the force applied is constant. All frictional forces are negligible. Okay, in addition to the spring scale, which of the 2 following quantities could the students measure with the equipment to determine the inertial mass of the cart? Inertial mass of the cart is the M in F equals MA. M equals F over A. F in this experiment is the scale, the spring scale reading. We need A. Well, in order to get A, we have to use 5, 4, 3, 2, 1. We know the initial velocity is 0, we need the time, and we need the distance that we go. So those A and D. C would be great, but we can't use the material that was given to us to directly measure the acceleration of the cart while in motion. The average speed of the cart. What is the average speed? Average. Well, That would be delta x over time. That could give us an answer. But what else does it equal? 1/2 times velocity initial plus velocity final over or multiply times time. Let me confirm why this one doesn't work. I haven't thought about that yet. What am I trying to find? I'm trying to find acceleration. If I know the average, I can't measure average speed. What, in addition to the scale, which of the two following quantities could the student measure? How do you measure average speed with a meter stick and a stopwatch? You can't. You can't measure the initial velocity. It's 0 in this case, but final velocity with a meter stick and stopwatch. Yep. Nope. Can't do it. Okay, moving on. Last one. I got 2 students. They're standing on top of a skateboard. They got rolly things, so we'll assume minimal friction of that wheel to the ground, but I don't think that matters. But listen to this statement. In order to get the student skateboard system to accelerate, second sentence, they have defined the system to you, the student skateboard system. In order to get this system to accelerate that way, I have to have an external force on that system. You can't have internal forces create an acceleration of itself. Okay, so the student X claims that student Y should apply a force on student X while both students stand on the skateboard. Well, if she applies a force on X, X will apply a force on her. Those are all internal. They cancel each other out. There's no acceleration going to occur. That's not an external force. Now, which of the following statements is true regarding that student's claim? So her claim is Y should push on X. The claim is correct because Newton's law states, second law, F equals ma, that an object will accelerate if a net force is applied. That is not a net force acting on the system. The claim is correct, which by the way is incorrect, and I would have quickly made the determination that their claim is wrong and then go straight to D and C to determine which one. But anyway, the claim is correct because student Y can apply a force that is greater in magnitude than the frictional force that are exerted on the student skateboard system. Once again, the student may be able to do that, but she cannot. There is no frictional force acting on it. They're standing at rest. So if they're not moving and they're not on an incline, they have no force of friction acting on them. C, the claim is incorrect because student Y cannot apply a force that is greater in magnitude than the frictional forces. Again, same thing. There is no frictional forces acting on it. D, the claim is incorrect because both students are internal to the student skateboard system. That is true. And internal forces within a system cannot cause the system to accelerate. I don't know if I did a good job explaining that, but I hope you understand. If not, please come see me.